Hello, everybody. My name is Francesco Melchiori, and I'm a product manager and data scientist in Phoenix. Phoenix is an IT and consultancy company of the Würth Group. The headquarters is in Italy, and we have customers all around Europe, mostly in Italy and in Germany. We are the developer of a unified monitoring solution, which is called NetEye, and it's powered by Icinga. We are actually Icinga partners. It's a long way to the system diagnostics. Today, I'm going to present our solutions for anomaly detection and anomaly prediction of IT systems. But our final and most ambitious goal is to pursue a solution for the diagnostics, which means having a solution that is able to point out the root causes of an issue in a general IT system. We face networks like this one. For example, this is a network that provides dynamics AX to the final end user. On the left side, you have users, and there is a broker that provides the remote desktop connections to those users. And underneath, there is the backend of the application, so basically the AOS, the application object server, which is basically the logic underneath the application. And finally, at the end of the chain, on the right side, you have a single point SQL server. We provide an architecture like this to our customer. On the customer side, you have the customer network, and there is a telegraph installed on each host. And basically, telegraph can get measurements from each host and puts everything in NetEye, which is powered by Icinga. This is on the customer side. On the Phoenix side, we have a data center, and thanks to a NAT iOS channel, we can synchronize the data between the customer and our InfluxDB in-house. Above InfluxDB, there is Grafana. Basically, every single node gives us a huge amount of metrics. For example, this is the remote desktop layer, and we get measurements like, well, processor, memory, disk, network, and system. Actually, there are lots of units of measurements under every single measurement itself. And that's for the remote desktop layer, for the application object server layer, and finally for the SQL server layer. This is actually a quite small network. Imagine having a huge network with, well, hundreds of nodes. But finally, we can provide to our customer a set of dashboards. Well, from one side, we can traction the final value to our customer. That means a customer can see a chart for every measurement, but on the other side, there is too much graphs, too much charts around. And it becomes really complicated to analyze the situation, the general state of the system in case of an anomaly. So we think that we need to process that big amount of data. And we choose the Python data science stack. So basically, well, we crunch data on the back end. And our solutions are based on Python, and we use mainly three different open source packages. The first one is NumPy. NumPy is able to, well, map your data into the so-called tensors. A tensor is simply a matrix, a multidimensional matrix. On NumPy, there is pandas. Pandas can transform those tensors in the so-called data series that are quite easily to manage because they have indexes, time indexes. And finally, we use scikit-learn, which is an open source package that packs lots of the most powerful machine learning algorithms out there. Honestly, for an audience like this, I don't know how much you know about machine learning. I tried to squeeze the very basic concept of machine learning in just one single slide. Well, I've got an entire library of books in my house talking about machine learning, so it's ambitious, but anyway. First of all, machine learning is not a marketing buzzword. It's a real technology based on solid mathematical concepts. And what does it mean, machine learning? Machine learning works on the so-called multivariate spaces. That means from a source of information, you can get multiple signals. One signal is a feature of that source of information. And one feature is a time series, basically. And if you slide an entire chunk of signals, you can get data samples from that data source. So basically, you can take data sample by data sample and put them in the solution space where every single feature is a dimension. In this super basic example, you have just a couple of dimensions, D1 and D2. And then there is a couple of machine learning approaches. One is the unsupervised learning, and the other is the supervised learning. The first one is when you have your data samples, but no labels. So you put your data samples in a space, and you can train with examples, with information, your algorithm in order to get a separation of clusters of data. Or if you are in the domain of supervised learning, you have labels for every single data sample. So the problem in this case is to separate groups. But, well, at the end of the day, you have a classifier. What does it mean? You can get an unknown data sample, and you can run it in the classifier, in the trained classifier, and the output is the group or the label of that sample. Machine learning algorithms work on a huge amount of signals, and there are lots of amazing practical applications. I want to give you just an idea. Well, if you are a Jedi, you can code email spam filters. You can design medical devices to predict epileptic seizures or heart attack, or even you can classify Earth scans to track the health of threatened habitats. On the other side, if you are Sith, you can customize super annoying advertisements to bother your website guests. Or even better, you can crawl social networks, scrape political posts, train fake news, train fake pictures, train even fake videos, and finally you can hack the democracy of the country you dislike. In our case, we use machine learning for anomaly detection, which is, if you remember well, our first goal. In this case, we take data host by host, and our data samples are from the past 2 weeks. The sampling period is of 5 seconds, and in this case, we use unsupervised learning, which is called an algorithm which is called isolation forest. So basically, we train the classifier every day with a cron job, and every 10 minutes, we are able to classify new data samples. So the output of this toy is a rate about the normality or the abnormality of a data sample. If it's between 0 and plus 0.5, it's a normal state of our network. Otherwise, if the rate is between 0 and minus 0.5, is an abnormal one. So we can plot this output, and now it's definitely easier for, let's say, an expert analyzer to browse the charts and finding the root cause of a problem in the entire network. Thanks to Grafana, you can explode chart by chart, looking at them at more and more resolution. But today, we move forward, and we are developing a new model, an anomaly prediction one. So in this case, we do not get any more data host by host, but we process data from the entire network. Because the data in this case is quite big, we applied a so-called principal component analysis in order to reduce the dimensionality of the problem. So basically, we are going to filter in the most relevant feature of the entire problem. And because we have labeled data, we are used supervised learning, the classical supervector machines, But that's the problem, because, well, I got a data sample that represents data of all the network with a label that is taken a while after the event. But that's a problem, that's a dilemma. So how can I get that label? Because, well, it is infeasible in a manual way to label every data sample. It's obvious, but of course there are several projects, there are different networks, and of course it's a real-time application, it's a real-time solution. How can I do this? Well, in Verphoenix, we have developed a tool which is called Alivix, and is a tool for that is able to visual synthetic monitorize a host. What does it mean? It means that Alivix is able to work on graphic interfaces. You can synthesize the behavior of your user. So basically, Alivix is a robot that is able to grab frames from a screen, detect the graphical patterns that you defined, and basically click and type in exactly in the same way that a real user would do. And finally, the most important part is that Alivix, it's a measurement system. It gives you the measure of how much a transaction takes to appear. Alivix is a graphical user interface tool, and you can design any application transaction with that. So basically, if you have a regular end-user interaction flow, that is a list of transactions, but you can define every single transaction with Alivix exactly from the graphical, the visual point of view. So basically, you can list Alivix objects, and that's exactly a so-called test case. If you run a test case, you can pilot, you can automatize any application, any graphical user application on your screen, and you can get measurement transaction by transaction. So this is an example. Alivix can run a browser, find a pattern, click in, type there, and reach the final destination of a user interaction flow. So you can check the availability of a transaction, if it is available or not. And most importantly, you can have the responsiveness of that transaction. So basically, how much the transaction itself takes to appear on the screen. The final output of this tool is something like this. So if you can schedule with Icinga an Alivix test case forever, continuously. So basically, you can consume continuously a graphical user interface on your host, on your synthetic host in this case, and you can get the transaction performance of all these steps, and you can correlate directly how much is good or how much is bad the performance of the entire network. because as you can see, you can get the latency spikes if transactions takes too much, or you can get even the service downtimes. So if I can put a linear threshold on these measurements, and finally I can map these measurements with my labels. So we really think that we can use Alivix synthetic users to fill the gap. And finally, we are developing and we are providing a solution like this. So with the original network of the customer, our Alivix hosts, and our data processing stuff. And finally, we are pretty much sure that we can raise an early alert in case something will be wrong. I wanted to thank you for your attention. If there are any questions.
So, do you have any questions? Oh.
Hi.
Hello.
Very interesting.
Thank you.
I just want to understand, the scikit-learn takes its input from the NumPy.
Not exactly. I'm sorry for the slide, but the pipeline is, well, NumPy, pandas, and scikit-learn.
Okay. And NumPy creates this tensor that you described.
Exactly.
Okay.
It's not so trivial because there are lots of, well, gaps to fill. I mean, you have to manage gaps in the data sources. You have to manage the sampling rate. Of course, you can have a signal from your processor, and you can have a signal from Alivix, for example. In the first case, you have a point every, let's say, millisecond. In the second case, you have a point every minute. So you have to, well, to think about the design of the entire pipeline in order to, let's say, extract the correct information and use it as a data sample for the machine learning algorithm.
And maybe this is a stupid question. This
No.
pipeline that you just described, is that like an alternative or something similar to Prometheus in terms of analyzing trends and predicting failure?
I'm sorry, but I don't know. I don't know what Prometheus is.
Okay. Thank you.
You're welcome.
So, I saw there was someone else somewhere.
So hi, I
Hello.
would just like to know what's like the accuracy of your trained models?
The accuracy.
Yeah.
Well, do you mean the anomaly detection or the prediction? The solution for the anomaly prediction. Well, in the case of the detection, honestly, I don't know what the accuracy is, because if you want to run a benchmark for machine learning, you need to have labeled labeled samples from an expert, you know.
Yeah.
So because of that, we are developing a tools for human in order to manually label a kind of data samples like that one. It's not trivial because in this case, the data sample is a stack of a certain amount of signal. So from the design point of view of the solution, we need to develop something that allows humans to put a label on a certain time frame, basically. And but that's the right question. Of course, we need a benchmark for that. Otherwise, let's say, I can tell you just about my sentiment, my feeling. We are in the right direction. I would say 3 out of 4 times the results are good. 1 out 4, so 25% of the anomalies are false.
Okay, thank you.
But you're welcome.
We have time for one more question. All right then. Thank you very much,
Thank you
Francesco.
very much.